Hello everybody. In this video we are going to be looking at the solutions for the College Prep Magnetism Practice Problems 1. Let's take a look at the first problem. We have a 1.20 centimeter wire carrying a current of 0.80 amps perpendicular to a 2.40 Tesla magnetic field. We want to know what is the magnitude of the force on the wire. So we are given the length of 1.20 centimeters. We do need to convert that to meters. So 1.2 centimeters is equal to 0.0120 meters. We are given the current of 0.80 amps, and we are given the magnitude of the magnetic field at 2.40 Tesla. And we are looking for the force. So if we are given the length of the wire, the current, and the magnetic field, and we are being asked to find the force, we are going to want to use F equals ILB. We're already solved for force, so no rearranging of the formula necessary here. We just plug our known values in, and we should get a force of 0.023 newtons. Problem number 2. A 24 centimeter length of wire carries a current and is perpendicular to a 0.75 Tesla magnetic field. If the force on the wire is 1.80 newtons, what is the current on the wire? So here we are given the length of the wire, 24.0 centimeters. Again, just as in the previous problem, we need to convert that to meters. So that is going to equal 0.240 meters. We are given the magnitude of the magnetic field of 0.75 Tesla. We are given the force of 1.80 newtons, and we are being asked to find the current. Once again, we want to use F equals ILB. In this case, we want to solve for current. So solving this formula for I will give us I is equal to F divided by L times B. Plug in our known values, and we should get a current of 1.0 times 10 to the first amps, or 10 amps. Problem 3. A 0.50 centimeter length of wire carries a current and is perpendicular to a magnetic field as shown in the diagram. They want to know what is the direction of the force acting on the wire. So again, we're going to use our right hand rule, so we need to use our right hand. I'm going to be using my left hand because the camera basically acts as a mirror, so I need to show you kind of a mirror image of how to do it. So we're using my left hand. I know that my fingers represent the direction of the current. My palm represents the direction of the magnetic field. So the magnetic field is coming straight out of my palm. So if I had an arrow going straight out of my palm, that would be the direction of the magnetic field. And my thumb is in the direction of the force. So if I want to orient my hand the way that it shows in the diagram, I need to turn my body a little bit here. But I know that the magnetic field is pointing upward, so my palm wants to be pointing straight up. The current is, by the way, that is 2.6 amps, not 26 amps, but the current is moving in the positive X direction or to the right. So you can see that my fingers here are oriented to the right. And my thumb back here, my thumb is pointing away from the screen or out of the page. So that is that is the positive Z direction. So the force is in the positive Z direction. Then they want us to find the magnitude of the force on the wire. And for that, let's take a look and see what we are given. We are given the length of the wire at 0.5 centimeters, which again converted to meters is going to be 0.0050 meters. The current is 2.6 amps. The magnetic field is 0.75 Tesla, and we are being asked to find the force. So using F equals ILB, I plug my known values into the equation, and I'm going to get a force of 9.8 times 10 to the minus third newtons. Problem 4. An electron beam is perpendicular to a 0.020 Tesla magnetic field. What is the force experienced by one electron if the beam has a velocity of 9.8 times 10 to the third meters per second? Let's take a look and see what we're given in this problem. We are given the magnitude of the magnetic field at 0.020 Tesla. We are given the charge because we know that we are dealing with an electron. I know that the charge of an electron is 1.60 times 10 to the minus 19th coulombs. Notice I didn't put a minus sign in front of that. I know that the charge of an electron is actually negative 1.60 times 10 to the minus 19th coulomb. But remember, with these problems, we are using the formula and the math just to find the magnitude of the force or for any of the other quantities. We're using the right-hand rules to find the direction. So usually we use positive and negative signs to denote direction. That doesn't matter with these problems because we are using something else to find direction, namely the right-hand rules. So we can ignore the negative sign for these problems. And lastly, we are given the velocity of 9.8 times 10 to the third meters per second. We are being asked to find the force. So for this problem, I need to use the force is equal to QVB, the charge times the velocity times the magnetic field. I plug my known values into that problem, and I should get a force of 3.1 times 10 to the minus 17th newtons. Problem 5. A proton experiences a force of 6.9 times 10 to the minus 15th newtons when it travels at a right angle to a 1.35 Tesla magnetic field. What is the velocity of the proton? Once again, I know because I am dealing with a proton that my charge for a proton is 1.60 times 10 to the minus 19th coulombs. I know that the force is 6.9 times 10 to the minus 15th newtons, and the magnetic field is 1.35 Tesla. I'm being asked to find the velocity. So in this problem, I need to use F equals QVB. Rearranging that formula to solve for velocity will give me V equals F divided by Q times B. Plugging in my known values to that equation, I will get a velocity of 3.2 times 10 to the fourth meters per second. Problem 6. We have an electron traveling at 8.6 times 10 to the 7th meters per second at a right angle to a magnetic field experiencing a force of 2.9 times 10 to the minus 11th newtons. They want to know what is the strength of the magnetic field. So again, because we are working with an electron, I know that my charge is going to be 1.60 times 10 to the minus 19th coulombs. I know that that electron is traveling at a velocity of 8.60 times 10 to the 7th meters per second. And the force is 2.9 times 10 to the minus 11th newtons. We are looking for the strength of the magnetic field. Once again, we need to use F equals QVB. In this case, we are solving for the magnetic field. So rearranging the formula will give us B equals F divided by Q times V. I plug in my known values to the equation, and that will give me a magnetic field of 2.1 Tesla.